So now we are going to tidy up the last little bit. We're going to prove that the loop actually finishes. Okay, so this is the while theorem. And we already discussed partial correctness, how to prove that the loop is correct if we assume that it actually finishes, that eventually the loop guard becomes false. For total correctness, we need to prove a little bit more. And here is the idea. How do you reason through that the loop completes? Well, usually you have some quantity, often the loop index, that is incremented or decremented every time through the loop. If it's incremented every time through the loop, usually there is a bound on how big it can get. Usually you have a for loop where you say for I equals 1 to n. That means I is incremented every time through the loop. It eventually is equal to n, and therefore you know that the loop is going to be executed a finite number of times. In other cases it might be that a loop index is decremented. In yet other cases there is some other means by which to reason that the loop is going to be executed a finite number of times. By convention, we're going to assume that whatever quantity is going to tell us that eventually we will finish, that quantity, or bound function as we will call it, will decrease every time through the loop. Now this is a convention, and we're going to make the convention that whatever the function is that decrements every time through the loop, it is actually bounded below by 0. And that's where this t greater than or equal to 0 comes from. The second part there says that if we are in the loop, if the loop invariant and the loop guard are true, then we're going to think about what this bound function is at the top of the loop. We're going to assign it to a dummy variable, a temporary variable in which we're going to hold the value as it was. Then we're going to execute the body of the loop, that's the command S, and then we're going to require for the bound function to have decreased in value, which means that it now needs to be less than this t prime that was the temporary variable that held the original value at the top of the loop. So that's the approach. Now our loop usually looks a little bit more complex in that we have an initialization command indicated by s sub I. Okay, so here's our prototypical example that we've talked about so much. And what this example does is that it sums the entries in the array B. We've created some space in which to doodle so that we can explain what this whole bound function idea is all about. Now let's think about it. We know that when we're in the loop invariant and the loop guard are true. So we know that k is less than n. So now we know two variables that appear in the loop, k and n. And what we want to do is think about a function of k and n such that that function is bounded below by 0 and such that that function decreases in value every time we execute the loop. So let's think about it. K less than n means 0 is less than n minus k, and that obviously means that 0 is less than or equal to n minus k. So that is what we mean by the bound function, this n minus k. It is bounded below by 0. And we can kind of look at this and say, and it's going to decrease every time we go through the loop because k is going to increase every time we go through the loop. So this is a very good candidate. So what do we know? We know that 0 must be less than or equal to n minus k at the top of the loop. What else do we know? This gets a little bit more complicated. Well, we have n minus k. We want to show that it decreases when we execute the statement s. And how would we reason through this? Well, we would say, well, before we execute s, n minus k has some value. And then after we execute s, that value has decreased by 1. So here what we're saying is, let's use a dummy variable, a temporary variable at t prime, and let's store in it what n minus k was before the execution of command s. And then let's check after the execution of command s whether n minus k is now less than this stored value. That's the basic idea. So all we now have to do is check two things. We need to check whether the loop invariant and the loop guard implies that this function that we chose is greater than or equal to 0. And we can instantiate what we chose to be that function. n minus k, and we can instantiate g. Usually the loop invariant isn't all that important in this discussion, although sometimes it is. And we ask now the question, is it the case that k less than n implies that n minus k is greater than or equal to 0? And we can then formally prove this. On the right we can apply algebra to come up with k is less than or equal to n on the right of the implication. We can then separate out k equals n, and then we end up with a classic case where a weakening strengthening law applies and leaves us with true. Then we move on and we ask, is it the case that this Hort triple holds? How do we prove that that Hort triple holds? Well, we need to prove that the loop invariant ng implies that the weakest precondition of t being assigned to t prime followed by the execution of s puts us in a state where t is less than t prime. We can instantiate what we chose for t and what the command s is. That gives us a composition of 3 assignments for which we now need to compute the weakest precondition. We do a textual substitution of k plus 1 for every occurrence of k in the post condition. We do a textual substitution of s plus b of k for every occurrence of s, and notice that there is no occurrence of s, so that's easy. And then we do a textual substitution of n minus k for every occurrence of t prime in the predicate. Now notice that all along we did not instantiate the loop invariant or the loop guard, and that's often the case, and that can save you a lot of writing. So now we do a little bit of algebra, and we find that we need to check whether minus 1 is less than 0, and that's obviously true, and anything implies true, and therefore we know that the assertion holds. Now notice that not only should we indicate the loop invariant now, but we should also indicate what the bound function is when we present an algorithm. So here's sort of the worksheet that we have been using all along. We have the loop invariant in a lot of different places. We have the loop guard in a lot of different places. And now we have this bound function to deal with. Now notice that we only really need to indicate what the loop invariant is once, because we know where it then needs to be true. And we only need to indicate the bound function somewhere because we know what to do with it. And that means that often when people present an algorithm, they present it in the shortened version where the loop invariant is given just before the loop, as is the bound function.